Hi everyone, this is Maverick Pua, the chemistry guru. Now in this video, we want to go through a question involving structural elucidation for organic chemistry. Now structural elucidation questions in organic chemistry, basically we have a few unknown compounds and then they are related to each other by a sequence of reactions. So typically they'll give us an unknown compound given the molecular formula, maybe X, then X will undergo certain reactions to give me Y, and then they give us the molecular formula as well, and so on and so forth. So we will have a few unknowns. So what we are required to do for elucidation questions is, of course, first thing, to identify all the unknown compounds, and second thing is to explain all the observations that is being mentioned in the question. I think we will need to use a few exercises to run this through. So in this video, we will only talk about one exercise, and in subsequent videos, we will introduce more exercises for elucidation question. So we will also need to run through what is the thinking process that we will need for us to attempt such questions, because usually the weightage of elucidation question is pretty heavy, minimum about 8 marks, and sometimes it can go up to 14 marks. So in terms of the weightage of the marks, it is pretty heavy. So we would need to know how to handle such questions. So let's jump in at this exercise and then we run through the thinking process along the way. Alright, so the question is here. Now typically elucidation questions are given in paragraphs form, so it looks like a problem sum. But essentially this question is also like an elucidation question because we have a few unknown compounds, and instead of using words or sentences to describe the processes, they give us in terms of schematic. So essentially the way we handle this question, it is the same. Now what we have is, I have a compound F, C8H12O, and using KMNO4, which is an oxidation, right? You'll give me 3 different compounds, G, which is C4H6O5, and then H, which is C2H2O4, and then plus 2 carbon dioxide. Then subsequently G will be heated with corn H2SO4 to give me I, which is C4H4O4, which is further oxidized to give me J, which is C3H2O5 plus carbon dioxide. Then for H, it will be oxidized to 2 carbon dioxide. So also given, compound F will effervescence with sodium metal, but does not react with warm acidified potassium dichromate. So we want to explain all the observations given here. And then of course, ultimately we want to solve back, identify all these unknown compounds, and then we piece everything together to form back the compound F. Alright, the first thing in terms of thinking process, what we will want to do is we want to think of the unknown compounds and then what are some of the possible functional groups that is involved in that compound. Now, actually this one depends on the scenario. If we notice that there are not a lot of functional groups present, then it is quite easy for us to have some possible functional groups present. Then it makes it easier for us to deduce the compound eventually. So for this question F, I think we can do that because it is C8H12O. So there's only one oxygen, right? So we can think of the functional groups that only contain one oxygen. Now in syllabus, of course, we will have alcohols and we will also have carbonyl compound. Now the question also gives us some information involving the chemistry, involving compound F. So compound F will effervescence with sodium metal. Now what reacts with sodium metal to give us hydrogen gas? In A-level chemistry syllabus, what we will have will be alcohols, phenol, and carboxylic acids. So in this case, it is possible to be a phenol, it's possible to be an alcohol, but it's not possible for it to be carboxylic acid because carboxylic acid has 2 oxygen, right? So I know that maybe you'll be an alcohol functional group or a phenol functional group. I can put this in here as a thinking process. So this will rule out the possibility that this oxygen, it is a carbonyl compound, so we can leave that out. Then the second thing is it does not react with warm acidified potassium dichromate, means that it doesn't undergo oxidation or it cannot be oxidized by dichromate. So if I have an alcohol and it cannot be oxidized by dichromate, then what you suggest is it is a tertiary alcohol, because primary alcohols can be oxidized to acid, secondary alcohols can be oxidized to a ketone. Tertiary alcohol, we know that this is resistant to oxidation. And of course, another possibility is a phenol. Phenol, it is also resistant to oxidation by dichromate, but we do know that F will undergo oxidation to form smaller fragments. Now F can be oxidized by KMnO4 to smaller things, G, H, and 2 carbon dioxide, so not likely there's benzene in F, so therefore the alcohol in F shouldn't be a phenol, but it is a tertiary alcohol. Now what we also notice is the close carbon to hydrogen ratio in F, so we will also notice that. And what this means is alkene will be present, so most likely we will have a few C-double-bond-C present, which will explain the high degree of unsaturation in F, and this reaction with KMnO4 most likely will be oxidative cleavage to give me G, to give me H, and to give me carbon dioxide. So later what we will need to do is we will have to figure out what is G and what is H, and then systematically we will have to add all these back together to give me compound F. Alright, so coming back to here, our deductions so far involving F is, I know that I have a tertiary alcohol, and I know that because of the high degree of unsaturation, I will have some alkenes present, but the quantity of it, we actually don't really know, but we will have to figure that out later. So up to now, this will be the deduction that we have for F. Now the next thing we want to do is we also want to analyze this particular process, F oxidized by KMnO4 to G, and 2 carbon dioxide. I know that if there are alkene functional groups present in F, then this reaction with KMnO4 will be oxidative cleavage and the C-double-bond-C will break, and depending on the groups that is attached to my alkene carbon, the products of oxidation of alkene will be ketone, acid, or carbon dioxide and water. So these are some of the possible products that can be formed. So what this means is if I look at the product G, H, and CO2, obviously, I can try to figure out what are some of the functional groups that will be present in G, in H, and later it is easier for us to figure out what these two compounds will be. So at least let me write down the process. I know that this is oxidative cleavage of alkene, and I know that the products of strong oxidation of alkenes will be ketone, acid, or carbon dioxide. So if I look at the products for G, which is C4H6O5, so maybe let me write this down first. G has C4H6O5. So what are some of the functional groups that can be present in G? Now, if I have so many oxygen, then most likely I'll have acid functional group. And if it is an odd number, then at the beginning we will be thinking that, okay, if it is an odd number, then it has to be a ketone, because the product of oxidation of alkene has to be ketone, acid, CO2, and water. Then acid has 2 oxygen, ketone has only 1 oxygen. So this guy looks like it is a mixture or a combination of 2 acid plus 1 ketone. So let me write down the acid first, because I think that one is valid. I know that most likely I'll have 2 acid groups. It will be present. Now, the other guy, which accounts for that 1 oxygen, will it be a ketone? Now, what we have to remember is earlier, our deduction is my F, it has a tertiary alcohol. Now, tertiary alcohol, it is resistant to oxidation. Even KMnO4 cannot oxidize that tertiary alcohol. So what this means is, if I come back to G, which has an odd number of oxygen, so most likely the tertiary alcohol will come to this guy here. So the odd oxygen, instead of a ketone, which is under normal circumstances, right? But in this case, it should be the tertiary alcohol. So let me put this guy in. I will have a tertiary alcohol inside my compound G. So far so good for this guy. Now for H, what we have is H, the formula is C2H2O4. If I have 4 oxygen, then most likely this guy, it is 2 acid groups. So I know that this has 2 acid groups. In fact, if I consider 2 acid groups, then C2H2O4 just nice, it will make up these 2 acid groups. The identity of F will just be ethane dioic acid. We can of course verify this involving the subsequent reaction of H oxidized by manganate further to CO2 and water, but we will talk about it in a while. But based on this observation, what we want to do is we want to deduce some of the possible functional groups of the products. I know that alkene oxidized by KMnO4, it will give me ketone, acid, CO2, and water. So based on the product, and then based on the number of oxygen, we can try to make some reasonable deductions in terms of the functional groups that are present in the products. Okay, next what we want to deduce is H. Actually it is fairly straightforward. As mentioned previously, C2H2O4, even if you do some random drawing, we can probably tell that C2H2O4 will just be ethane dioic acid. Now actually this is further reinforced by this reaction. Ethane dioic acid is one of the two acids in syllabus that can be oxidized by KMnO4 to carbon dioxide and water. Now in syllabus we have two acids that can be oxidized to CO2 and water. One is methanoic acid, 1 carbon acid. The other one is ethane dioic acid, 2 carbon diacid. So this guy, actually very easily I can just identify this. This will be an acid group directly bonded to another acid group. I can either write it as this, COOH bracket 2, or I can write this as H2C2O4, or I can also draw out the structure for this guy. This will be an acid functional group directly attached to another acid functional group. So the identity for H is determined. It is fairly straightforward. Alright, next what we want to do is we want to identify G, correct? So I know that the functional groups that is in G, most likely it will be 2 acid groups and 1 tertiary alcohol. And what is given further is it will undergo heating with corn H2SO4 to give me I. Now the difference between G and I, C4H6O5 and C4H4O4, you notice there's no change in the number of carbon. I'm losing 2 hydrogen, I'm losing 1 oxygen. So if I'm losing 2 hydrogen and I'm losing 1 oxygen, effectively what is happening is I'm taking away water, right? So this one is just taking away of water, and taking away of water will be an elimination reaction. Now considering heating with corn H2SO4, one possible reactions will be an elimination reaction of alcohol to form alkene functional group. So most likely what I would have is I will have an alkene, and the 2 acid groups that is in G will still be carried forward to I. So we can put this in if I consider I, which is C4H4O4. The functional groups present when G is converted to I is taking away water. So what I will contain now will be the 2 acid groups, should still be there, and now it will have a C double bond C functional group. Now on oxidation with KMnO4, this I will give me J, which is C3H2O5 plus CO2. Now what we will have to do is based on the products, and I'll try to reason out what is the identity for J, and then we link back to what is the identity for I. I know that this reaction with KMnO4, this is oxidation to give me J. Now J will be C3H2O5 and carbon dioxide. Now C3H2O5, what would this likely be? Remember there's only 1 alkene functional group in I, so therefore we only need to worry about the 1 oxygen that comes out of it. So I know that if I oxidize alkene, the possible functional groups will be ketone, acid, CO2 and water. So if I have this 1 extra oxygen, then what this must mean is the ketone is this functional group. So I know that this guy will be a ketone, and let me write this in. If it is a ketone, then what will the structure be like? Because I only have 3 carbon, so it is quite easy for us to try to draw out a reasonable structure for them. So if it is 3 carbon, then it is quite easy for us to draw out the carbon because it will just be a straight chain. And if it is a ketone, the ketone will be in the middle of the carbon chain. And I also know that there are 2 acid groups in J. So the acid groups, of course, will have to be on the terminal carbon. So this will be the first acid group, and this will be the second acid group. So for product J, we have already identified. So this will be what J would look like. Now what we will have to do is, of course, we will have to consider what I would be like. Now how do I work backwards and figure out what is the alkene present? Actually, it is fairly simple. What we know is this carbon, which is the ketone carbon, actually was part of the alkene, correct? So maybe I can highlight this so it is easier for us to figure this out. So this carbon is part of the alkene. Then how about CO2? Now CO2, it is the product of the oxidation of the part of the alkene, which is a terminal carbon. So this CO2 actually comes from the oxidation of CH2, and this carbon, actually it is a terminal alkene, because if this carbon is bonded to 2 hydrogen, then on oxidation by KMnO4, this group will be oxidized to CO2 and water. So therefore, the 2 carbons in an alkene are actually identified. So this will be one of the carbon of the alkene. This will also be the other carbon of the alkene. I can just join these 2 guys together and I can identify I. So let me try to put this here. If I combine these 2 together, I add these 2 back to try to identify I will just be carbon, carbon, carbon. Now this carbon will be C double bond. The other terminal carbon will be here. This will also be the other carbon. So if I put in the functional group, this will be a hydrogen and a hydrogen. And this is supposed to be an acid group. This is also the acid group. So this alkene on oxidation will give me J and CO2. So what this means is, this will be the identity of I. I will be this compound here. If we want to, I think it is also a good idea for us to verify the molecular formula as a way to double check our answer. C4H4O4. So I have 4 carbon, 1, 2, 3, 4. 4 hydrogen, 1, 2, 3, 4. 4 oxygen, 2 from each of the 2 acids here. So I has been identified. Now, we also need to go back, because once I've identified I also need to work backwards and to try to solve for G. Now G, it is an alcohol, and then it undergoes an elimination reaction to form the alkene. So what we will need to do is, we will need to put back water to I to form back G, which is an alcohol. Now actually there are 2 places where I can put the OH group, but remember G, it is a tertiary alcohol, so the OH group has to come here and the hydrogen has to come here. So if I work backwards, now moving back, what I can do is I can deduce the identity for G. Now for G, what I will do is, the rest of the carbon is effectively the same. Remember, I need a tertiary alcohol, so therefore the OH group should come to this carbon here instead of the CH2 carbon. So I will put an OH on this carbon, then this carbon on top will now become a CH3. This remains an acid group. The other carbon would remain an acid group. So G will be something like this, my tertiary alcohol. Alright, finally we have deduced G, we have deduced H. So what we want to do is, we want to piece everything together to figure out what is my final guy, what is F. Now, you notice what I've drawn here, it is a recap in terms of the oxidation of alkene. Now on strong oxidation of alkene with hot acidified KMnO4, depending on the fragment of the carbon and depending on the groups that is attached to the alkene carbon, it will be oxidized to different things. If it is a RR group, it will be oxidized to ketone. If it is a RH, it will be oxidized to acid. If it is a HH, it will be oxidized to CO2 and water. So what we want to do is, we want to make use of this and we work backwards. Actually, if I look at the product and I look back at the starting guy, how do I do the conversion in the first place? It is fairly easy. If I have a double bond, I just stick an oxygen, I'll form the ketone. If I have a double bond, I just stick an oxygen, and if I have a CH, I insert an oxygen between the carbon and hydrogen, it will become the acid. If it is HH, and then we will straight away convert it to CO2 and water. So if I want to work backwards and figure out what is the part of the alkene that can give me all these products, it is fairly easy. What I just need to do is, I just need to cancel away the oxygen. If this is the product, I cancel away the oxygen, this guy will become this structure. If acid is the product, I cancel away the oxygen for the C double bond, and I cancel away the oxygen for this COH. You notice you go back to this structure. If it is CO2, we just associate directly with terminal carbon CH2 group. So if I try to apply this idea here, then what we do is, if this is an acid group, I just need to cancel away the oxygen, then this will be the alkene that is on oxidation, that will give me my product G. Now remember, this tertiary alcohol, it is the original tertiary alcohol for F, so we will leave this untouched. On oxidation with KMnO4, this guy is not doing anything. So if this is acid, what I do is I cancel away the oxygen, cancel the oxygen. So later this will be the part of the alkene that will be oxidized. If it is a HH, same thing for the acid group, oxygen I cancel, oxygen I cancel. Then how about for our CO2? CO2 will be easier. CO2 will just be a terminal carbon. So same thing, working backwards, what will this structure look like before it is oxidized to G? So if I try to draw this fragment, remember this will be a C double bond and a CH. So I'll draw the double bond here, and this will be the CH. Now remember, this carbon is this carbon here, followed by a COH CH3. So let me put this in. This will be a COH group and a methyl group, CH3 group, bonded to this carbon here. This carbon is a C double bond O and a carbon bonded to a H. This will be a C double bond bonded to a hydrogen. So this will be the part of the alkene that will form G on oxidation. So this part, we are done with it. Now how about H? Now what will the part of the alkene be that will form this guy on oxidation? Again, what we do is we just cancel away the oxygen, and then I just draw this carbon ignoring the oxygen. This will be a C double bond O bonded to a hydrogen. So this will be a carbon bonded to a hydrogen. The other carbon is the same thing, double bond to a hydrogen. Then this will be a carbon double bond to a hydrogen. So this fragment on oxidation will give me H. Now, how about CO2? CO2, it is a terminal carbon, right? So CO2, this guy, will be CH2, but I have two of them. So therefore, this guy, I'll have one CH2 and I'll have another CH2. So I'll just draw two of them. So later it is easier for us to put them together. So basically, what we have is, I have all the parts of F, but it is all mixed up. I'll have this portion to give me G, I'll have this portion to give me H, I'll have two of these guys to give me carbon dioxide. So let me label each one of them. Maybe I call this fragment number 1, then I call this number 2, I call this number 3, and I call this guy number 4. So basically what I want to do is I want to piece all these 4 pieces together to work out a reasonable identity for F. And interestingly, and thankfully, fragment number 1, it is actually symmetrical. Fragment number 2 is symmetrical. So later, there will only be one outcome. If number 1 and number 2 is asymmetrical, then there can be a few possibilities. Now remember, fragment number 3 is on a terminal carbon, so probably it will be on the extreme left-hand side. So I'll put fragment number 3 first. Then it will be joined to either number 1 or number 2. It doesn't really matter because it is symmetrical, correct? So number 3 may be joined to number 1. Then number 1 has to join to number 2. It cannot join to number 4 because number 4, it is the terminal carbon. So it will join to number 2. Then finally, number 2 will join to fragment number 4. Now remember, because this number 1 and number 2 are symmetrical, so 3, 1, 2, 4 or 3, 2, 1, 4, effectively they are the same thing. Otherwise, it will be a little bit more complicated and we can have 2 possible answers. So if I'm drawing 3, 1, 2, 4, and what we want to finally do is to, of course, piece everything together. So let us try to do that. If I draw number 3, which will be something like this, terminal carbon, CH2, double bond. Then I try to draw fragment number 1, join to this CH, and then I'll draw the carbon with the tertiary alcohol. So this is the tertiary alcohol. Join to the other carbon, which is part of the alkene, CH, double bond. Okay, so I'm done with 1. Then I want to move on to number 2, double bond CH. So this will be a CH bonded to another CH, double bond. So I'm done with fragment number 2. Finally, I can move on to fragment number 4. This will be a CH2. So maybe to make it clearer, if I color code each of this guy, fragment number 1 is this. So remember, this is my fragment number 1. My number 2 will be this guy. So this is my number 2. Fragment number 3 is this carbon. So this carbon will be here. Finally, fragment number 4 is this chap. So this chap will be here. So therefore, this will be the identity for F. This is our compound F. Of course, it is a good idea to double check our molecular formula because F, it is a pretty big compound. I know that the molecular formula for F will be C8H12O. So let us try to verify that. I have 8 carbon, 1, 2, 3, 4, 5, 6, 7, 8. And hydrogen wise, I will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 hydrogen, 1 oxygen it is here. So therefore, this will be the likely correct answer for structure F. Alright, so that was the discussion involving structure elucidation for this exercise. Now you notice what we will need to do for us to do such questions is we have to be very, very familiar with all the reactions that is in syllabus, because we need to actually apply all the reactions that we learn to systematically deduce what are the functional groups present in the compound, and then we try to piece everything together to identify all the unknown compounds. So if we are not very familiar with some of the reactions, then very often we will get stuck, or we will not be able to identify one unknown compound. And then sometimes if I don't know what is the structure of one unknown compound, then it affects the identification of subsequent compounds. So that is usually the reason why students face some difficulties in answering deductive-based questions. So hopefully after going through this exercise, we have a slightly better idea in terms of an approach in elucidation questions. Of course, this type of question inherently it is a little bit difficult because it carries a lot of marks and it is intimidating. So what I will try to do in subsequent videos is maybe to find more appropriate examples, and then we run through more of these exercises. So if you have learned something useful from this video, please give me the thumbs up, like this video, and subscribe to my YouTube channel for more weekly video lessons. That's all for now. Thanks for watching.